Every year, millions of tons of textiles end up as waste due to the technical challenges of recycling them.
Majority of textiles contain different fibers, right? So most textiles are fiber brands, and the way we recycle textile fibers depends on fiber type.
But what if we could understand textile fibers so well, so precisely, that recycling them becomes smarter, faster, and more efficient? At Aalto University and VTT, a multidisciplinary team of researchers is transforming the way we measure and predict the properties of textile fibers.
We've developed a new patented technology to estimate the degree of polymerization in cellulosic textile fibers. And it's important because specifically in chemical recycling of cellulosic fibers, you need to monitor and control degree of polymerization to enable spinning new man-made cellulosic textile fibers.
This patented method combines hyperspectral imaging with machine learning. Traditionally, measuring this key property requires a lengthy laboratory procedure.
Well, traditionally you evaluate degree of polymerization as intrinsic viscosity, which is the standardized laboratory procedure. And I think it takes roughly 1 to 2 hours to complete in the lab.
The new approach reduces the time dramatically.
With our method, we can do it in less than 30 seconds.
To study recycling realistically, the team first needs samples that represent all stages of wear and damage.
For the chemical recycling of cellulose-based materials like cotton, modal, viscose, hemp or flax, and the degree of polymerization as well as the molar mass distribution are important factors. Those properties need to be managed and controlled to establish a trouble-free recycling fiber spinning process.
These molecular features influence how fibers behave during regeneration and spinning. The researchers at Aalto create this foundation by preparing a broad range of degraded fabrics.
We simulate the aging, or in other words, the degradation of textiles by the use of chemical treatment as well as laundering to provide samples of a wide and representative set.
At VTT, the spectral information is measured from the samples. Each pixel contains detailed optical data.
The hyperspectral image is measured by recording the light that is reflected from the fabric.
We use light in many different wavelengths. And when these wavelengths resonate with a specific type of chemical bond vibration, light gets absorbed. And in this way, we can actually produce an absorbance spectrum, which is basically like a fingerprint of the underlying chemistry of a material.
We then use the image spectra to train supervised machine learning models to predict the degree of polymerization for each fabric.
The process is rapid and doesn't alter the material.
And we have programmed a software to use the models to predict unknown samples.
To understand what drives fiber deterioration on a fundamental level, the team at Aalto uses a different form of light, X-rays, to examine changes at the nanoscale.
X-ray scattering helps us to understand the changes that happens in the nanostructure of the cellulose fibers, specifically in their crystallinity due to repeated washing or chemical treatments.
These measurements complement both imaging and modeling efforts.
We hope our results can explain the mechanism behind the degradation and how this degradation translates into changes in the properties and also in recyclability.
Interpreting spectral and scattering data requires a theoretical framework.
To help the data analysis, we use molecular modeling at VTT.
Simulations reveal how the fibers respond to aging.
So we use our models to predict how cellulose microfibril structures degrade during repeated laundering and drying cycles.
Together, the teams at VTT and Aalto are able to create a cohesive view of how cellulose fibers change through use and recycling. By linking experiments, imaging, and modeling, this project lays the groundwork for more reliable and scalable textile recycling. turning used fabrics into future materials.